In this video, we're going to do a review of basic derivatives, and we're going to stick with polynomials, and we're going to show you some applications of how you can use derivatives, especially in microeconomics. And we're going to make sure that you understand what a derivative means. So let's start with a basic polynomial quadratic equation here. Y equals 2x squared minus 44x plus 400. And take a derivative of it. The basic rule for taking derivative of polynomial terms is to take a term like 2x squared here, and what we want to do is multiply this little term here, 2x squared, multiply by the exponent, and then subtract 1 from the exponent. It's a simple rule that always works. So let's take the derivative. Now a little bit of notation. If you want to take a derivative of the function y, dy, with respect to x, dx, so dy dx, this just means the change in y as x changes, so d for difference or change, equals 2 times 2 is 4, so multiply by the exponent, and then subtract 1 from the exponent on the x, so 4x to the first. But we won't write the first because that just clutters up our notation. Minus, and then we take the next term. If terms are added or subtracted, you can treat them separately. So minus 44x minus, we take the exponent on the x, which is 1, multiply it by the 44, and that's just 44. And then we take x to the first. Let me write that over here. We take the x to the first, and we subtract 1 from the exponent. So what are we going to get? Well, x to the 0. So that becomes x to the 0 power. And anything to the 0 power is just 1. So all we're left with here is 44 times 1, plus the derivative of 400. Well, the rule is anytime you have just a number, a constant here, with no x terms in it, the derivative is 0. So we're left with the derivative 4x minus 44. Okay, why would we want to do this? Why is this interesting or an important thing to do? If you look at our notation here, that you use when you take a derivative, dy dx. This stands for change in y over change in x. In other words, what we're talking about is rise over run. A change in y. Let's look at this graph over here. This is a graph of this original function, 2x squared minus 44x plus 400. If you think about change in y over change in x, well, a change in y is just a rise, and a change in x is a run. And so if you have that ratio, change in y over change in x, it's a slope. And that is the whole point of taking a derivative. It's to find a rate of change. It's to find a slope. Now, to bring this home and make this very clear to you, one of the common uses is to try to find the place on a function like this. This is a parabola. We might want to know where is the place on this parabola where the slope is 0. So if we look at this blue curve here, the parabola, we can see that the slope is 0 or flat on the bottom here somewhere. And we can see, looking at the x-axis, that it's somewhere between x equals 10 and x equals 15. If you want to know exactly where the slope equals 0, this function tells you the slope for any value of x. So if you want the slope, which is 4x minus 44, if you want that equal to 0, okay, set that function equal to 0. Whoop, sorry, I left out a part here. Let me get rid of that. 4x minus 44 equals 0. What value of x is that going to be true for? Well, we can move the 44 over to the other side. 4x equals 44. Divide both sides by 4, and you're going to be left with x equals 11. And sure enough, if we go back to our graph, That's certainly a believable answer for where that slope of that parabola is going to be equal to 11. Now, what else could we do with this information? Well, we might not only be interested in knowing the x value, where the slope is 0, we might be interested in knowing the y value at this point on this parabola also. Perhaps this parabola is a total cost function, and right here we're going to minimize total costs at x equals 11. Now x could be an input, or it could be a number of units of output, for example. So if we use 11 units of x, what is our total cost? Well, then all we have to do is plug in x equals 11 into our original function here, and that'll tell us the total costs when we are minimizing, when total costs are lowest, which is at the bottom point of this parabola right here. So if we plug in 11 here, 2 times 11 squared, well, that's 2 times 121 minus 44 times 11. And 44 times 11, we'll just write it out here so we have everything together, plus 400. So 2 times 121, 242, minus 44 times 11 is 484. And then plus 400. What is that going to give us for that value? Well, let's look at the graph. I always like to get an estimate from the graph. Somewhere around maybe 155 or 160. So what are we going to get here? Well, the 400 and the minus 484, that's minus 84, so we're going to be left with 242 minus 84. Let me grab my calculator and see what that's going to be. 242 minus 84, 158. 158 is y equals 158 when x equals 11 at that bottom point of the parabola there. So hopefully you see how this can be useful, and by thinking about this parabola as being perhaps a total cost curve, minimizing total costs would be a very useful thing that we might want to do. Now, I don't want you to think that just because of this example where right here we were looking at where the slope equals 0, we're certainly not limited to that. For some reason, we might want to know where the slope equals minus 20, for example. Well, where is the slope equal to minus 20? Well, all we have to do is take this slope function, the same slope function, 4x minus 44 equals 20. So for what value will that be true? Let's add, oh, sorry, I actually said minus 20, didn't I? Okay, so 4x minus 44 equals minus 20. Then add 44 to both sides. We get 4x equals 24, and x is going to be equal to 6 right there. X equals 6. So that tells us that right here, where x equals 6, that slope of that parabola is minus 20. Now, how could we verify that? What if we didn't believe that or wanted to double check to see if that was true? Well, all we have to do is draw a line tangent to that parabola right at that point and try to see if it looks like, in the neighborhood of this point, that if we go over 1, that the rise over run is about 20 or minus 20. So between 5 and 6, if we go over 1, how far do we have to go up on that line? Let's look over here at the y-axis. Well, I believe that it could be between 200 and about 220 right there. So we have this run minus 20, sorry, rise of minus 20, and a run from 5 to 6 of 1. So it checks out. It looks like that's a believable answer. So let's practice a little bit what we know now and take it to a little bit more extreme kind of example. So if we have a polynomial, it doesn't have to be just a quadratic. We might have something like, say, 5 times, it doesn't have to be x, 5r to the 6th minus 4r to the 3rd plus 3r minus 100. And we can go even into negative powers, plus 3r to the minus 2, for example. We can use exactly the same rules to take the derivative of a function like this. Since they're all polynomials and they're just added and subtracted from each other, what's the rule again? Take the exponent and multiply by it. So we multiply this by 6 and subtract 1 from the exponent. So 6 times 5 is 30. Subtract 1 from the exponent, we get r to the 5th. Minus 4r cubed. Well, that's minus 3 times 4 is 12. R cubed becomes r squared. Plus 3r becomes plus 3. Minus 100, derivative is 0. We don't worry about that term, or it just cancels itself out. Plus 3r to the minus 2. Well, that's plus. Minus 2 times 3 is minus 6. R to the minus 2, we subtract 1 from the exponent. R to the minus 3. And keep in mind, it's easy to forget if you don't work with exponents on a daily basis, that this r to the minus 3 exponent says that this term is the same as 1 over r to the 3rd power, but times 6. So that's going to be minus 6 over r cubed is the same thing there. Now, another step we can take, and this is a very common thing that we have to do in a microeconomics kind of study, is to deal with exponents that are not integers. They're not like 6 or 3 or 4. We could have a little bit more complicated expression, but we use the same rules to take the derivatives. We could have 4.3 times, I'll just stick with the variable r, for example, 4.3 r to the 3.1 plus 2 times r to the 0.7. What if we wanted to take the derivative of this? Well, our notation, we would say, okay, the derivative dy dr equals, what do we do? Take the 3.1, multiply by 4.3. And we get 13.33. So 13.33 r to the what power? Subtract 1. 2.1 power. Plus 2 times r to the 0.7. Multiply by the exponent. It's the same rule. 1.4 is 2 times 0.7. Subtract 1 from the exponent. 0.7 minus 1 becomes minus 0.3. Sorry, times r to the minus 0.3. And again, we could rewrite this portion of this equation here, if we wanted to look like this. 1.4 over r to the 0.3. These two terms right here are exactly the same thing. It's just writing it in a slightly different way. Okay, I have two more ideas left that I want to quickly talk to you about. The next idea is the idea of partial derivatives. A partial derivative is when you have more than one type of variable in a function, and you want to check the slope with respect to one of the variables, how one of the variables is changing. For example, we might have a function like this, that say output Q is some kind of function of the amount of labor that we use, say to the 0.4, times the amount of capital that we're going to use, raised to the 0.6, for example. How do you take a derivative of this, first of all, normally what we're going to want to do is take a partial derivative. Let's take a partial derivative and then we'll talk about what that means. So a partial derivative, instead of using a d, we use a little curly d normally if we're taking a derivative of a function just with respect to one variable. Let's say L. We want to know the slope of how fast quantity increases as we change L. So we would write it this way. The derivative of how quantity is changing as we change L, so these are just curly D's or deltas, equals. What we do in this case is we treat everything that doesn't have an L in it, like this k to the 0.6 here, treat that just like it's a constant, the number 4, for example. And then we take the derivative of the term that has the L in it. So what do? Well, we multiply by the exponent, 0.4, times L, subtract 1 from the exponent, minus 0.6. And then that's just a constant, so we just keep it exactly the way it is, k to the 0.6. What if we wanted to take the partial derivative with respect to k? Well, that would look like this. dq dk equals. Now we're going to treat items with an L in it like it's a constant, so we can just write that without changing it at all, times the derivative of k to the 6. Multiply by 0.6, so 0.6 times k to the 0.6 minus 1 to the minus 0.4. And that's all we mean by a partial derivative. And what do they mean? Well, this function would give you an idea of how rapidly quantity is going up as we increase the amount of labor, because it's the slope as we change labor. And this function would tell us how fast quantity is increasing as we change capital, because it's the slope, the derivative with respect to capital there. Now, one more idea. Show you one more practical example about how we use derivatives a lot in microeconomics. Suppose we had a function like the following. And what we're talking about here is a total cost function. So total cost equals, it's a function of quantity. So maybe it is 3 times q cubed minus 4.44 q squared. And then maybe plus 5q plus 1, for example. And we wanted to take the derivative of this. Well, why would we want to take the derivative? A derivative of a total cost function tells us a marginal cost function. So we could say something like this. The derivative of quantity, sorry, that's not what I want to say. What I want to say is the derivative of the total cost with respect to quantity. And since this is just a normal derivative, technically speaking, I should use a regular d there. It's just a little picky bit of notation that you learn in a math class. Economists don't pay quite as much attention to it, but I'm probably going to get in trouble for saying that. Take the derivative of 3q cubed and you'll get 9q squared minus 2 times 4.44 is 8.88 times q to the first plus 5. What do we have now? Well, we have the marginal cost function, which tells us for each additional unit we produce, how much does it cost? In other words, it's the slope of total cost. The slope of total cost is marginal cost. And sometimes we don't emphasize this idea enough in economics classes. So for example, if I wanted to know the marginal cost of producing the third unit of output, we'd plug 3 into this function. So plug in 3, q equals 3. What's the marginal cost? 9 times 3 squared, 9 times 9 is 81, minus 8.88 times q. 8.88 times 3 equals 26.64. And then plus 5. simplify this down, and what we're going to get is 59.36, or we'll call it $59.36 to produce the third unit of output of this product. And this same principle works for if we had a function for total utility, the derivative is marginal utility. Derivative of total cost is marginal cost. If we had a function for total benefit, this would be marginal benefit. If we had a derivative for, say, a total tax rate or total tax, the derivative would be marginal tax rate or marginal tax owed for a particular case. And so hopefully by seeing and practicing these few little examples of derivatives and keeping in mind that a derivative is a slope and that the derivative of a total function gives us its slope, which is the marginal of that function, you'll be better prepared for your microeconomics classes.